This is part 3 of the notes on acids and bases, and in this part of the video we are going to talk about the relationship between ion concentration and pH, the pH scale, and also the pOH scale, and how those things are related. So we talked in the last video about how to find the concentration of hydrogen or hydroxide ions using the ionization constant of water. There's a ton of scientific notation involved. You're dealing with very, very, very small numbers, generally speaking. At least 2 out of 3 numbers are usually very small. And so those scientific notation values get cumbersome, and it's easy to get mixed up with the exponents. And if you try to write them out in standard notation, you can lose a zero here and there. So the pH scale is a logarithmic scale. Now, what does that mean? In this case, the logarithmic, it's a base 10 logarithm. And what that means is any number can be written as 10 to the power of something. So the exponent, the x in this number, is the logarithm. So when you take the log of a number, what you're finding out is what power would I raise the number 10 to? To what power would I raise the number 10 if I wanted to get this for an answer? So that's all we're doing. We're basically calculating the exponent to which a number to which the number 10 would be raised in order to find a specific number that we want. And we can find any number, any positive number using this. So what we're going to do is we're going to take the log, the base 10 logarithm of the hydrogen ion concentration, and we're going to take the negative of that value because this is going to give us a negative number, because these numbers are all negative exponents of 10. So just to make it a little more straightforward, and to put everything in a positive scale, we're taking the negative of the base 10 logarithm of the hydrogen ion concentration, and that's called the pH. So, for example, what is the pH of a 0.25 molar HCl solution? Like we talked about in the last video, HCl is a strong acid, which means all of those HCl's are going to dissociate to produce hydrogen ions. So we can use the molarity of the solution as the concentration of the hydrogen ions because it's a strong base. So to find this number, we're going to take the negative of the base 10 log of the hydrogen concentration, which we just said is 0.25, the same as the concentration of the solution. And when we do that, we find that the pH of this solution is 0.6. Now the pH scale goes from 0 to 14. Think back to the last video, the ionization constant of water is 1 times 10 to the negative 14. That's not a coincidence that the scale goes from 0 to 14. Okay? The lower the number, the closer to 0, the more acidic it becomes. The closer to 14, the more basic it becomes. Pure water, which is neutral, is a pH of 7. So 7 is neutral. Anything lower than 7 is an acid. Anything greater than 7 is a base on the pH scale. Now, what is the pH of a KOH solution? Okay, so now we've got KOH, which means it's a base, an Arrhenius base. So we can't directly take the log of this number to find the pH. But if we go back to thinking about what we did in the last video, we know that the ionization constant of water is 1 times 10 to the negative 14th, and that equals the hydrogen concentration times the hydroxide concentration. This is a strong base, so we can assume that the hydroxide concentration is 1.3 times 10 to the negative 2, same as the concentration of the solution. So that means we divide both sides by 1.3 times 10 to the negative 2, and we would find that the hydrogen concentration is equal to 7.69 times 10 to the negative 13th. Okay, so when we can take the negative log of that number. Okay, so there's just an extra step here because we have to use the OH, the hydroxide concentration, to find the hydrogen concentration, and then we can use that to calculate the pH. When we do that, we find that the pH is 12.1. So that's a number above 7, much closer to 14. which makes sense since we're talking about a basic solution, a solution with a bunch of hydroxide in it. So the pH equals 12.1. And I just want to make a quick note to remember these two numbers. We had 0.6 as the pH of this solution, which was 0.25 molar HCl, and we have 12.1 as the pH for a 1.2 or 1.3 times 10 to the negative second KOH solution. So 12.1 and 0.6 are a couple numbers to keep in mind as we move forward. Now, we can also do what's called the pOH scale. It's just not as commonly used. We use the pH scale for acids and bases because they both fall between 0 and 14 on the pH scale, but we do have something called pOH, which is just taking the negative log of the OH concentration. So what is the pOH of that same 1.3 times 10 to the negative 2 concentration KOH solution? Well, since we have the OH and we're looking for the pOH, we can just take negative log of that concentration. We don't have to find the hydrogen concentration because we're doing pOH instead of pH. So we take the negative log of 1.3 times 10 to the negative 2, and we find that the pOH equals 1.88. Now, what's the pOH of a 0.25 molar hydrochloric acid solution? Right, so that's the same solution that we started with on the last slide, and we found the pH of that, which was 0.6. Well, we can go through the same process we did before, where we say, okay, 1.00 times 10 to the negative 14th equals the hydrogen concentration of 0.25 times the hydroxide concentration. When we do that out, we find that the hydroxide concentration is equal to 4.00 times 10 to the negative 14th. Okay, so we take, so the pOH is the negative log of 4 times 10 to the negative 14th, and that equals 13.4. Okay, so remember I asked you to remember a couple of numbers. The first number was that the pH of this solution, the 0.25 molar HCl, was equal to 0.6. That's from the last slide. Well, the pH of this solution, which we found on the last slide, was 12.1. And it was actually 12.11 and change. Well, if you take a look at these two things, 13.4 plus 0.6 equals 14. 1.88 plus 12.11 equals very close to 14. The reason it's not 14 is because we've done some rounding along the way. So here's a fact that you can take advantage of. The pH plus the pOH always equals 14. Why do you care? Well, because if you had a question like this one, right, what is the pOH of a 0.25 molar HCl solution? You could do what we did here, right? What we did down here was we used the kW of water, 1.0 times 10 to the 14th, and we found the hydroxide concentration, then we took the negative log of that. Okay, you could do that. It's not super complicated. But the other option would be, say, all right, since this is HCl, I know it's an acid. I know the pH is the negative log of 0.25. Take the negative log of 0.25, 0.6, subtract it from 14. You'd get 13.4. Okay, so if you have the pH and you want the pOH, subtract the pH from 14. If you have the pOH and you want the pH, you subtract the pOH from 14. So you can always find it that way, which just saves you a little bit of work with the scientific notation. Again, that's a little bit of a pain. That's why we use the pH scale. So this would just save you some work along the way. Now, those are all strong acids and bases. What happens when it's a weak acid or a weak base? I'm going to show you an example with a weak acid, and you would do the same thing if it was a weak base. And again, if you're doing pH, POH, you can do the minus 14 thing, or 14 minus at the end. But the difference, again, between strong and weak acids and strong and weak bases is that weak acids or bases don't dissociate completely, which means you cannot use the concentration of the solution in the logarithmic calculation. You have to use the log of the ion concentration, which is not the same as the concentration of the solution if it's not a strong acid or a strong base. So now what? Well, we're told in this problem that the dissociation constant of this solution, acetic acid, acetic acid, that's the stuff in vinegar, is 1.77 times 10 to the negative fifth. And we're told that the concentration is 0.1. Well, that means that the concentration of the acetic acid is 0.1. So this is 0.1. Well, that's the concentration there. Now, the concentration on the other side, we don't know, but what we do know is that since, just like we did in a couple of other examples we've done on worksheets and things like that, the two products come from one source, which means whatever the concentration of the hydrogen ions is also the concentration of the conjugate base on the other side. So the concentrations of these two products are going to be the same, x and x, which means we're going to end up with an x squared. So here's how we're going to set this up. We're going to use the dissociation constant, and we're going to use the concentration of the acetic acid to work out what the concentration of the hydrogen ions would be, and then we can find the pH using that. So here's the equilibrium expression, right? The concentration of the hydrogen and the conjugate base divided by the concentration of the acetic acid. There's no exponent, no coefficients here, so no exponents, which means that the dissociation constant, which we were given, is equal to, so that's what we were given, 1.77 times 10 to the negative fifth, is equal to x squared, whatever the concentration was. Remember we said it was x and x, so x squared divided by the concentration of the acetic acid minus whatever the concentration of the dissociated ions would be. So it's not exactly 1 molar because at equilibrium you've lost some of that acetic acid into ions. So we take the original concentration, we subtract whatever the concentration of the hydrogen ions would be. That would give you the new concentration equilibrium. Now, here's a little bit of a trick that we're going to use. Since the concentration of these ions is going to be extremely small, okay, it's going to be somewhere in the order of, several magnitudes, orders of magnitude below 1. So it's going to be essentially 0. And there's a guideline to follow this, but we're going to assume that it's close enough to 0 so that it's going to be basically insignificant in terms of subtracting it from the 0.1. It's not going to make much of a difference. So we're going to leave that as 0.1. So if this is really going to be pretty much 0.1 minus 0, then to solve we would divide both sides by 0.1. Okay, multiply, because this is already divided. And we end up with 1.77 times 10 to the negative fifth times 0.1 equals x squared. So we solve for that, and that x equals 1.33 times 10 to the negative third. Okay, a really small number. Now that is the hydrogen concentration. It's also the other concentration, but what we care about is the hydrogen concentration. Now we have a value that we can log to find the pH. So there we go. pH is the log of 1.33 times 10 to the negative third, and that gives us a pH value of 2.88. It's an acid solution, so that makes sense that it would be below 7, and it's about halfway between neutral and the strongest acid, which makes sense for this particular concentration. Okay, acetic acid is somewhere in the middle of the acid range. So we talked about this a couple of slides back, but the relationship between pH and pOH. First of all, if you're looking at the scales themselves, they are opposite of one another. So a 0 on the pH scale is equal to 14 on the pOH scale, and vice versa. 14 on pH is equal to 0 on the pOH, or on the pOH. And 7 is the same for both because it's neutral on both scales. So they go in opposite directions. But the other key factor that we talked about is that the pH plus the pOH always, always, always equals 14. So you can always use that fact to find one if you've got the other. So that's it for this video. In the next video, we're going to talk about neutralization reactions and a process called titration, which is using known concentrations of acids or bases to find the concentration of an unknown acid or base. So that'll be the last video on acids and bases coming up next.